All right, so here's our first Bernoulli's example. All right, so this is going to be pretty straightforward on picking the initial and final points. Sometimes, I think you may remember with conservation of energy, sometimes that could be difficult choosing the proper initial and final points. So we'll start with one that's pretty easy to choose the initial and final. It is going to involve a little bit of your continuity equation there with that constant volumetric flow rate, so we'll involve that. And hopefully just get an idea at how the formula works. Now, you may mention that up here I've changed my H's to Y's. That's because that's the way that it's written in your AP formula packet. I used H's in the previous video so that it was easy to connect it to the height, as in the gravitational potential energy. However, on the AP exam, they use Y's, and the reason why they use Y is because if you'll remember, when they did pressure, they did rho GH, and H was the height of the water above you, and they didn't want you to get confused with that, to think that, oh, it's the same, I need to know how much is above me. No, this is how high are we physically. All right, now that is going to affect the pressure and things, obviously. But you'll see as we go. But that's why AP uses a different letter there, is to actually help you remember that they're talking about something different here than when you have the rho GH of the pressure because of a depth in a fluid. All right, connected, but not exactly the same thing. All right, so here we go. We got water circulating through a house in a hot water heating system. Water's pumped at 0.5 meters a second through a 4-centimeter diameter pipe in the basement under 3 atmospheres pressure. What will be the flow speed and pressure in a 2.6 centimeter diameter pipe on the second floor, 5 meters above? And it does say assume it's a single pipe, so it's not a pipe that's branching into other pipes, because obviously that makes it a little bit more complex, because you'd have to look at each of those individual areas rather than just a single area. Now, hopefully you recognize the fact that the size of the pipe is changing. We talked about this a little bit in the previous video. This is the first thing you did with fluid dynamics. So what we're going to do is we're going to first find out what is the flow speed. What's the speed of that? Okay, now I'm hoping that you're recognizing, oh yeah, this is that continuity thing. So A1 V1 equals A2 V2. And so the area, it is a pipe. It does say diameter. Because it says diameter, we're assuming it's circular then. And so the area will be pi r squared. So pi times the radius, which will be 0.02. Now, I did 0.02, number one, because this is diameter. So I need the radius for my pi r squared. The other thing, I went ahead and turned it into meters. In reality, it doesn't matter as long as these two are the same. Those two, the units are going to end up canceling anyway. But because we have that habit of writing it in SI, I'm going to go ahead and put 0.02. Recognize that there are 2 sig figs here, 2 sig figs here. It looks like all of my data points have 2 sig figs, even though AP doesn't care about it anymore. They do kind of care about it, it's just they're not going to count off for it. So I'm going to do my best to try to stick to 2 sig figs in my answer. The work, I'm not going to take time to include all those zeros. Okay, velocity 1, which was that 0.5 there, equals area 2, which will be that pi times the radius in the diameter later, which so 2.6, so 0.013 squared, and then times my new velocity, which is what we're solving for. Okay, so at that point, you should be able to punch this into your calculator, divide by these numbers, and get the answer. So here we go. And I get V2 is equal to 1.2 meters per second. Hopefully that makes sense. The diameter is not quite half of what it was. The diameter is squared, so if it was half, it would be 4 times bigger. So it would be 0.5 times 4, which would be 2. This is less than that, so I'm okay. It's greater than what I had before because it's smaller diameter, but it is less than quadrupling that. And so I'm okay with the answer that I have here. Okay, so velocity 2 equals 1.2 meters per second. All right, now the second question is, what is the pressure? I know you're thinking, Mr. Bauer, this is supposed to be Bernoulli's equation. You're doing all this other stuff. So now we're going to use Bernoulli's equation. Now, what clues us off that it should be Bernoulli's equation? Well, think about this. If you draw a picture, it starts with the pipe down here in the basement, and then it goes up to a different pipe on the second floor. Now, that should be reminiscent of the picture that we drew in the last video where we were talking about Bernoulli's equation. So down here, you're going to have a certain pressure, you're going to have a certain velocity, and you're going to have a certain height, which again we're going to label as y. And then over here, you're going to have a different pressure, velocity, and height. Okay? Now, remember, we can define height 0 to be wherever we want. And so generally speaking, it makes sense to make 0 be right down here at the lowest point, just like when we did conservation of energy. So I'm going to make that 0, which that's going to help us out just a little bit as we go. All right, so what I'm going to do now is I'm going to take my equation and I'm going to rewrite it down here so that all my work is in one place. And then we're going to go through each of those pieces, see what we got, and hopefully we'll be able to solve for our final answer. All right, so come with me. Let's rewrite that. All right, so what do we got? What do we got? We can identify this as being point 1, initial. This is point 2, final. So from here, pressure 1, we know pressure 1. That's the pressure in the basement. That's the 3 atm. Now remember, we do want it all in SI, and so look at your formula packet. There is a thing that says 1 atm is equal to 10 to the 5th pascals, and pascals is our units for SI. So we're going to use pascals here. Okay, so we do know P1. P1 is going to be 300,000 pascals plus, and we'll go 1/2 times the density. Now the density is water, and remember water we assume is 1,000. And then times our initial velocity, velocity 1, which is what we were given at the beginning, that 0.5 squared. Now this rho gy is based off of the height of point 1, which we've defined that as 0. And so that's actually going to be really nice. This is going to be 0 because the height y1 is 0. And so that's going to go away. So then we can just go straight into equals pressure 2. That's what we're looking for. Plus 1/2. Density again is 1,000 times the velocity squared. That's what we just found. Good thing they asked us to do that first. So 1.2. Recognize that they may not have that as a part A. They might not ask for the velocity at 0.2, and you would have to recognize, oh, the pipe's changing diameter. I'm going to have a new speed. I better do this first, and then I'm going to go ahead and do my Bernoulli's. All right, and then we have plus, again, the density, 1,000, times G, which is 9.8, and then times the height, which that's what it told us right here, that it's 5 meters above where it was in the basement. And so we'll go ahead and put the 5 in there. Okay? Again, I'm just going to write 5. I know it's 2 sig figs. And you'll notice that at this point we have everything we need in order to be able to solve for pressure number 2. So, pull out your calculator, work it out. Let's see what we get. And I got 250,405 pascals. All right, now, does that make sense? Well, it is going faster. If it's going faster, it should be lower pressure. It is higher than it was before, which means there's less water on top of it. Again, should mean lower pressure. So those things together, we should end up with a lower pressure compared to the pressure that we had before, which was that 300,000 pascals. So yes, it's less. Notice that it's still higher than a single atmosphere. You want that, because if the pressure here is less than an atmosphere, it's not going to be able to come out, right? If you're using this to heat your water for your shower, you want the water to be able to spray out, so there needs to be some pressure behind it. And so therefore having extra pressure there is obviously a good idea. Okay, so there you go. There's your first example with Bernoulli's. Pretty straightforward. Got to use a little bit of the continuity equation there. And hey, join me in the next video. We'll do another one.